Recording in progress.
Okay, good. All right. Good morning, everyone. Welcome to the last lecture of this semester. Good. There's a few housekeeping things maybe we have to do. So the first thing is I promised there's gonna be another, or I had promised there's gonna be another quiz. So I just threw a quiz together yesterday, which we will do at the end of this lecture as before, or we're gonna do it within 10 minutes. Yes, and I think we said the exam is on the 27th. Is this correct? Let me quickly check if I already gave a time, because that's actually exam. Okay, we said at 10. Good. I'll still have to confirm with my secretary that this is all, that there's no collision with any other thing happening. Good. So yes, one thing we should do maybe is gonna be a Q&A session where we can also do a few exercises before the exam. So the exam is on the 27th, which is a Thursday. So how about pending that there's no collision with any other events, I would say we're just gonna put this on the typical lecture spot, Monday the 24th, right? I don't see hands going up in complaints. So good. So we'll come together here, the 24th then, and gonna go through some potential material that could be in the exam, right? Still pending on how many people register for the exam. And yes, then yeah, you will have an opportunity to ask any remaining questions. Good. So last time we again had to move to the, yes, there's a question.
Sorry, so if it's going to be all or written exam will be covered on the 24th.
No, already before that. I mean, I'm gonna probably let's do that also. I'm gonna open. Okay, so today we're gonna have the second quiz, right? I'm gonna correct this later today with. Probably I don't need help for that. Dangerous words, but I'm gonna exam registration. Good. Whoever is qualified can then register anywhere between probably tomorrow and in 2 weeks, right? And then seeing, actually, yeah, let's say 10 days, something like this, a appropriate time frame, and depending on how many people are then registered, we will decide whether it's going to be an oral exam or a written exam. That's actually a very good point. Thank you. Okay, good. Okay, are there any more question on related subject matter?
If I may, I don't know.
Of course.
So now the summer semester of 2023.
That's a long time ago. Okay. Nabil, yes, there was a former postdoc of mine who's long. I mean, who actually left in 2023. So.
And he and yourself gave a class called post-quantum.
He gave the course. So yeah, I think I helped out once, but he did this all by himself.
I see, and there will no be.
No, I mean so first off, I'm going to teach together with Lucian Hanslik the crypto lecture in the upcoming summer term, right? So that in itself takes a lot of time, and yeah, I mean I don't like to have an extra small lecture when I teach a big lecture like that. But I mean, basically, what you're getting right now with this lecture here is a teaser of what post-quantum crypto is about. But what we could do, if you're interested in that subject matter, is we could do a seminar in the upcoming summer term. I would just ask my current postdoc, Mahesh, to take the lead on that. So if they, I mean, we can maybe let's do a hands up. Who would be interested in a 1, 2, 3, 4? Okay, so good. Then I'm gonna meet him later. Then we can already. Good. Okay. No, that's good. Then there will be more in-depth treatment or insights into these topics. Okay, but now I think we're already 10 minutes into the lecture. Let's maybe get started. So last time, right, I wrote a few on the few of these slides on the blackboard. Of course, that's why I shouldn't, or common problem with me when I'm writing stuff on a blackboard, I might get carried away, go off the rails. And I think we didn't get very far, right? We got to the definition of the learning with errors problem. Good, which essentially, let's repeat that here, ask for the following, right? I think I went pretty much off the rails comparing this to number theoretic hardness assumptions, right? So in learning with errors, you're being given a uniformly, no, I wanted red, a uniformly random matrix A chosen from some finite ring ZQ, some modular ring ZQ, right? Q is just a sufficiently large integer, no special property, doesn't have to be prime, doesn't have to be a product of primes or anything. And good, that's just a random matrix over a finite ring. It could be prime, right? Sort of this can be sometimes be helpful, but let's put this away. Could be helpful if it is prime, right? But not needed for the hardness of the problem. And now S is a uniformly random vector. So E is now chosen from this error distribution chi. And what I said is this distribution chi outputs samples or numbers. What do we do here? Yeah, in this case, we sample from chi to the m, right? That is, we just draw m independent samples from this distribution and write it into a vector. But the key feature is that these when we look at these error terms as integers, not necessarily mod q, you can always embed them in ZQ by reducing the mod q, but as integers, they should be small, right? And if they're sufficiently smaller than q, then reducing mod q doesn't even do anything, right? Good, so chi is the error distribution, and u is a uniformly random vector. So the search LWE problem, you can maybe think of that as an analog of the D-log or better CDH problem as the following. I'm going to give you this matrix A and A times S plus E. And your goal is to find this secret S, right? Looks somewhat similar to D-log. In a D-log problem, you're being given a generator. Right now, I'm writing the same stuff that I wrote on the blackboard. You're getting G and G to the S, and the question is to return S. Or, I mean, it's, again, closer, I would say, to the CDH problem, where you're being given G, comma, H, G to the S, H to the S, and the goal is to find S, right? But here, the hardness in the setting of LWE, the hardness does not come from the hardness of inverting this homomorphism, this exponentiation, the hardness of D-log in essence, but from solving linear equation systems with noise. If we left the noise away, this would be an easy problem, right? If you just gave me A and A times S, then solving this is just Gaussian elimination. Textbook thing that hopefully every single one of you learned in your math course in the very first semester, right? Gaussian elimination is the absolute core algorithm for almost any discipline in computer science, right? Gaussian elimination is the base algorithm. But Gaussian elimination is not stable with noise, right? So this already shows up when you want to numerically solve an equation system on your computer using floating point integers, right? If, I mean, again, depending on whether you took these courses, there are properties of equation systems that are called, say, the condition number. Or if you look at linear equation systems over the reals, there's, you look at the maximal singular value and the minimal singular value, and now the condition number is just the fraction or the quotient of those two, right? So if, in particular, the minimal singular value, and singular value, think of eigenvalues, right? A singular value is just the singular values are just the eigenvalues of matrix multiplied with its own transpose, right? If the smallest singular value is too small, right, to kind of fit into your floating point arithmetic, then you will necessarily see rounding noise, right? Then your computer has to discretize the computations, and that will lead to noise. And if the smallest singular value is too small, you're just going to get a garbage solution when you run Gaussian elimination, right? Then there are some tricks to do numerically stable linear algebra, but comes with its own problems. And here, this LWE problem is, let's say, the errors don't come out of our arithmetic. No, they just come from the outside. We want to do crypto, right? So we can add errors. And now, please find S given AS plus E. This is a hard problem. And as I kind of alluded to last time, it's as hard as worst case lattice problems, right? So the cool thing about LWE is you can do crypto from the hardness of lattices without using a lot of, let's say, lattice math. I mean, this looks similar, if you recall, to how lattices are defined, but we're computing over a finite ring ZQ here, whereas lattices are necessarily infinite objects. Right? So we're taking the hardness from some a large family of infinite problems or problems defined over an infinite domain and sort of condensing its hardness into this nice finite problem. Right? Of course, if finding S given A and AS plus E is sort of like the CDH problem, then there should also be a DDH problem. And in the case of LWE, this is just, I'm going to give you A and AS plus E. I'm going to ask either this, or I'm going to give you A and a uniformly random vector U, chosen uniformly from ZQ. And I'm asking you, which one is it, right? You have to decide, did I just give you an LWE sample or just something uniform, right? And whereas in the world of groups, we always explicitly have to make the DDH assumption, right? It doesn't follow from the CDH assumption. Here in the world of LWE, the decision assumption follows from the search assumption, right? You just have to assume the hardness of the search assumption, hardness of decisional assumption follows. This is not a trivial reduction. It uses a few clever ideas such as hardcore bits, right? Which I cannot go into now, but that's a cool aspect of this field of crypto, right? That everything, the whole hardness goes back to these worst case lattice problems. You don't have to always make new problems and assume they're hard. Typically, you can find reductions between them. Good. And what really controls the hardness of the LWE problem is this ratio between the modulus Q, right, and the error bound B. Right, the smaller this quantity is, the harder the problem. Right, I mean, we said earlier that that B should be smaller than Q half. So this fraction is at least 2, right? But for if it gets as low as 2, we're not able to do crypto with this problem, right? Because then it's almost information theoretically hard. So we're typically talking about much larger values of this problem, at least something polynomial in the security parameter, but sometimes even sub-exponential in the security parameter. Good. And this is, I'm not saying how this is called. This is called the modulus, modulus to noise ratio. So noise ratio. Good. As I said, for if n the dimension of the problem is sufficiently large, we can show that both the search and decisional LWE problems are as hard as worst case approximation problems in lattices. Good. In a way, I already talked this through right now, how this compares to number theoretic problems. And yeah, again, a crucial difference between LWE and the number theoretic crypto we've seen is that in number theory crypto, the anchor of hardness, where also hardness flows from, is the hardness of the D-log problem. If discrete logarithms were easy, there's no number theory crypto, right? Whereas in LWE, it's not about inverting a homomorphism. It's about doing linear algebra with noise. In a way, it's the hardness comes from this geometric problem, right? And linear algebra becomes kind of geometric once you consider noise, right? Or noise that is small, right? And if there was no noise, then inverting or finding S given AS is easy. Good. And as I said, the hardness of LWE depends on this fraction or this ratio Q divided by B. The bigger B, the harder the problem. But one can also see will also be able to see the smaller we make B, that is, the larger we make Q divided by B, the more functionality we can get. Right, so in lattice space, this is one takeaway. Whereas in number theory crypto, it's always a 0-1 thing, right? You're getting some functionality, and either you can prove security of your scheme or you cannot. Whereas in lattice crypto, it's kind of always a trade-off, right? To get more functionality, you want to make B smaller or Q to the B larger, but that will weaken the security. Right? I mean, this can be stated in a quantitative way, but in lattice-based crypto, there's always a tension somehow between functionality we can achieve, and the hardness or the security of the resulting scheme. Good. And this is really having a trade-off between functionality and security. We're still talking about I mean, we're not talking security goes away completely, but we're talking going from potentially exponential security going to something like sub-exponential security, right? Does it take an exponential time adversary to break my scheme, or can a sub-exponential, even quasi-polytime adversary break my scheme? This is really in very strong contrast to number theory-based crypto, right? Where your scheme is either secure or it isn't. There is no parameter that you can crank up or down, right? Whereas in the world of lattices, there is this parameter that allows you to kind of fine-tune hardness versus functionality. And that's typically, again, by choosing B somewhat small. Okay, good. Now let's talk about how we can build public key encryption from this LWE problem. And that's Regev's encryption scheme. And Regev encryption is, in essence, just the analog of the El-Gamal encryption scheme, a somewhat, one could say, natural analog. So let's look at the Regev scheme. I don't know if I already wrote that last week. But good, let's look at this. So we have this is just a public key encryption scheme, and we're just going to show CPA security, right? This scheme is not CCA secure, if any one of you would like to know. So, of course, we can build CCA secure schemes in very, very similar fashions as we built them from number theory assumptions. But again, today's the last lecture. That's now beyond our scope. Good. So what does key generation do? Kind of the obvious thing, right? To use LWE, we need a matrix A and kind of some LWE sample AS plus E. And guess what? My encryption algorithm just generates these two guys. So it generates a matrix A and a vector B, which is just AS plus E. And my public key is just A comma B, right? Not really hard. And what's a good choice for secret key? It's my S, right? My secret S. So let's see. What else could I have chosen as a secret key? Yes, maybe. So then would this have made things different, or yes? Yes.
As soon as you know either S or E.
That's true, but good. Let's say I'm gonna tell you S, right? I'm gonna you're having S as a secret key, and I'm also gonna give you the public key A and B. So what does that mean about E? Yes? We can compute it, exactly. Just by computing B minus A times S. Right? We compute B minus A times S, that's E. So if you give me the public key and S, I can compute E. How is it the other way around if I give you the public key and E? What about S? Exactly. So what you would do is when you're being given A, comma B and E, right? Then B minus E, we know this is just A times S. And here we just do Gaussian elimination or whatever, right? Solve, right? We also know A and get S. Good. Okay, so that's the key gen, right? And before even moving on, right? What does the LWE assumption tell us about public keys of this scheme? The decisional LWE assumption. We're not going to. This is an encryption scheme. We're not going to use the search assumption, right? To build encryption schemes, it's usually better or more convenient to use decisional assumptions. What does the LWE assumption tell us about the public key? Yes. It looks pseudo-random, exactly, not just B, right? A and B look like independent uniform, right? So A is always chosen uniform, but then in the real scheme, we're choosing B dependent on A. But LWE tells us, look, this B looks like it was just chosen independently and uniformly random of A. So A comma B is just a bunch of uniformly random values. One arranged in a matrix, the other one arranged in a vector, but that doesn't change anything about them being uniformly random. Okay, cool. So how do we encrypt with this scheme? And here's something interesting happens, right? Our message is just a bit. That's not the interesting part. But here we're just gonna choose a uniformly random vector, a vector of uniformly random bits. That's the important thing, right? Recall our matrix A looks somewhat like this. We're having N here, M there, and M is sufficiently greater than N. So we're just choosing M uniformly random bits. And we compute C1 is just X transpose times A, and C2 is X transpose times B plus Q over 2 times M. Right? This is really just simple arithmetic. If you look at encryption here in this scheme, right? If it wasn't for these, let's say, dimensions of the matrix A, right? We're going to have to use cryptographic parameters. So think of N as something like, I don't know, 4096 or 2048, and M, let's say, 50 times that. Right, so we're even for let's say, moderate sizes of the modulus Q, this matrix will be of size megabytes. I'd compare this to an Elgamal public key, right? Let's say instantiated with one of these very compact curve like ed25519. There, the size of the public key is essentially less than a kilobyte, right? So we're talking about public keys of size 1 kilobyte versus potentially tens of megabytes, right? So now you already know the main drawback of these schemes, right? So even though in theory this doesn't really make a difference, in practice, to instantiate these schemes securely, we will kind of need that the public keys, secret key can be very small, right? Secret key you can kind of generate as pseudo-randomly. So secret key, you can store it using 128 bits, but the public keys are like a factor 1,000 bigger than that of number theory-based schemes. And one can argue, right, for many devices like, I don't know, desktop computers, servers, and whatnot, this doesn't really matter anymore today because, I mean, we're constantly taking pictures that have sizes tens of megabytes and sending them around. But there's also, I mean, these, let's say, standardized encryption schemes also have to work on very weak devices, like on IoT devices, embedded devices, and whatnot. And for those dealing with keys that are that have size order of megabytes is an issue, right? So considerable effort has been invested into coming up with versions of these schemes, right? Actually, versions of the underlying hardness assumption, where the matrix A has a very compact representation, right? I mean, from the talk that I now just gave, the keywords are ring or module LWE, right? There you can bring the sizes of the public key actually down to a few kilobytes, but you're making sort of a stronger hardness assumption on a much more, not just on worst case lattice problems, but worst case problems in structured lattices, something like called an ideal lattice, where ideal doesn't mean it's perfect. No, it's the mathematical concept of an ideal, right? It's like an additive subgroup of a ring, or which commutes with all elements multiplicatively. Something which you can reduce modular, where you can do a modular reduction with and get another ring. But I'm getting off track again. So we've just discussed the encryption algorithm. Now let's look at the decryption algorithm. So the decryption algorithm gets to touch this secret S, and it just computes C2 minus C1 times S. And now this is a value in ZQ, right? And in ZQ, there's different ways of representing these modular integers, right? We can either represent it as something between, let's say, 0 and Q minus 1, right? Oops, not G, ZQ. This is the standard representation, but another one is we're going to just take the upper half of those and shift them down, right? We represent the upper ones as negative numbers, right? We can also represent it as, let's say, minus Q half until Q half. Right, let's just assume for the moment that Q is even. Also works if it's not even, you just take the next one. Good. That's called the central residue class representation. Good. And now, once we've done this, once we've represented this z in minus q half to q half, we just check if the absolute value of z as an integer is smaller than q divided by 4. So we're going to output 0, otherwise 1. Good. And as a first thing, as always, we will first look into correctness of this encryption scheme, right? We've seen from all the number theory constructions that we had, typically correctness is a property that goes like this, right? It's just checking one, maybe maximum 2 equations in groups. Cool, these 2 values are the same, so scheme is correct. Now, again, I said in lattice-based cryptography, there's always kind of a trade-off between functionality and security, which even in the simplest scheme, in regef's encryption scheme, the consequence is that showing correctness is not like this, right? So even, I mean, correctness is functionality of a scheme, right? And it's not going to be complicated, but you have to sort of think a bit, why is this scheme even correct, right? And what this little lemma here says, that if 4 times b times m, and m is now not the message, that's a bit stupid, m is this parameter here, right? If 4 times b times n is smaller than q, then the scheme is correct, meaning that decryption of an encryption of m again returns m. Good. Now let's look into the proof. I should have done maybe some builds here, but at least it's already written up. So we know that it holds in this scheme that B is of the form AS plus E, where E is an error vector sampled from chi to the n. Right? So that means each component of EI of E is sampled from this distribution chi, right? EI follows chi. And since chi is B bounded, it means the absolute value of EI is smaller than B. I don't know if I said smaller equal earlier, but doesn't really matter here. So let's say it's smaller than B. And now let's take ourselves a ciphertext, C1, C2, where C1 is X transpose times A, C2 is X transpose times B times Q half times M, right? Even for that, to compute this Q half times M, I need, for now, actually not strictly necessary, but let's assume Q is even. But I already said earlier, let's assume Q is even, so that this is again a proper integer value. Interesting that no one asked, but wait a second, if Q is odd, then you're not getting an integer here. There's ways to deal with this, and it's a very simple way. You just round to the nearest integer. Right? Whenever in lattice schemes you're getting a non-integer value, you just round to the nearest integer. Right? So really a lot of things that you do in lattice-based crypto have a very strong fixed point arithmetic flavor to them. Okay, cool. And last thing that we recall is X is sampled from 0, 1 to the M, right? It's a binary vector. And decryption takes C1 and C2 and first computes this value Z here, right? C2 minus C1 times S. So let's do that, right? Let's compute C2 minus C1 times S and plug in the expressions for C1 and C2. So C2 is X transpose times B plus Q half plus q half times m. It's already rearranged here. And C1 times S is just X transpose times A times S. Is minus, sorry. No, I think good. Right, we said C1 is just X transpose times A, and C2 is X transpose times B, this vector B, right? Recall that, let's also put that here, B is a vector of length M. X transpose times B plus Q over 2 times M. So this is correct. Okay, so now we've plugged in C1 and C2. Next thing, we're going to plug in the expression for B, right? So B is AS plus E, right? So now let's apply distributivity of the inner product or matrix vector multiplication. I mean, it's just really just an inner product. X transpose times AS plus E is the same as X transpose times AS plus X transpose times E, right? And once we're here, we can see this X transpose AS term cancels out, right? Recall, if we go back to El Gamal, the same thing happens there, right? And once this has canceled out in El Gamal, we were left with, or a term like this has canceled out, we were just left with the message M. But here now, we're gonna get the message M times Q half plus this X transpose times E, right? So we're having this bit M plus X transpose times E. And now let's maybe look how this kind of looks graphically. Let's see if it actually lets me draw a circle. Ha, it does. Good. You can always represent a modular ring kind of as a circle, right? We're gonna put 0 here. Then let's say 1 is here. We can go around the circle, and at some point we arrive at Q minus 1. And if you add 1 to Q minus 1, you get Q, and Q modulo Q is 0, right? So this is why this is also called a cyclic group, right? Because you can nicely represent them as a cycle. Good. And if we draw it like this, then Q over 2 is here. Okay. Now get a different color. So if my message M is 0, right? Then I know, good, then Q half times M is 0, and I'm adding this term X transpose times E. What I'm going to show in a moment is that this X transpose times E is small, right? It has a small absolute value. That means my ciphertext is somewhere close to 0. Right? I can either go a little bit to the left or a little bit to the right, but I'm not going to go too far away from 0. Whereas if my message is 1, then I'm starting with Q half and adding a little bit, right? So I'm going a little bit in this side or a little bit in that side, but not too far, right? So what I really need now is to make this not too far concrete. So here I have Q over 4, and here say minus Q over 4, which is the same as 3/4 Q, right? What I really need is that I don't move past these points. If I can make certain that this let's say, a decryption error here, X transpose times E, never gets larger than Q over 4 in absolute value, right? Then I know if I started from a 0, then I will, and add the error, I will always be closer to 0 than to Q over 2. And the reverse is also true. If I start from Q over 2 and add an error, I will not jump across this boundary, right? This is not gonna happen, and I'm gonna stay in this region around Q over 2. Okay, and if this is the case, then my rounding algorithm or my decryption algorithm actually works. So, because what does the decryption do? It takes this Z, the value we've just computed, right? This Z here, and checks if if the absolute value of Z as an integer is smaller than Q over 4, right? Basically tests whether we're in this region up here, right? This is Z smaller Q over 4, and if so, decrypts to a 0. Otherwise, right? Otherwise, we must be in the second case. We must be somewhere around Q, in this region around Q over 2. It decrypts to a 1. Okay, so really the last thing to do here is to check whether this is actually the case. If this decryption error X transpose times E is actually smaller than Q over 2, well, let's compute it, right? We can this inner product X transpose times E, that's just the sum of Xi EI. Let's just throw the triangle inequality onto this. No fancy stuff like Cauchy-Schwarz needed here. And sometimes we do need Cauchy-Schwarz, which is the slightly more advanced version of that, but nothing like that used here. And triangle inequality of absolute value says is that the norm of the sum is smaller than the sum of the norms. And norm or absolute value is multiplicative, right? What's absolute value of xi? Well, we know this is smaller than 1, right? Because each xi is either 0 or 1. So those guys are all at most 1. And the EIs, they're all smaller than B. Right, so in total, since we're going I equals 1 to M, 1 to M, and also here 1 to M. So we're summing up M terms that are each smaller than B. So the total thing is smaller. Let's make here, this is, whoops. Come on, here. This is actually proper smaller than B. So the entire thing is smaller than M times B, right? Good, that's the size of the error. And we said the scheme is correct if this error is smaller than Q over 4, right? Then if this error that's introduced by decryption never surpasses Q over 4 in absolute value, then decryption is always going to decide for the correct value. Good. And now let's just let's recall that we required that Q is bigger than 4B times M, right? In this case, it holds that, well, M times B, so the norm of, we've seen X transpose E is smaller than M times B, right? On the other hand, we had this Q over 4, right? But we said Q is bigger than 4BM. So we know that Q over 4 is bigger than B times M or M times B, right? Those two guides are the same. So since Q is greater than 4BM, it always holds that X transpose E, the absolute value of that, is smaller than Q over 4, and therefore our scheme is correct. Decryption algorithm always returns the correct value. Good. So that's good. All right, that's correctness, right? Not as, I mean, not insanely difficult, but not as trivial as El-Gamal encryption or even Kramer-Shoup or whatnot. Here we had to work a tiny bit more. All right. So to prove security, I'm just gonna import not a hardness assumption, but a statistical tool called the leftover hash lemma, right? I'm gonna discuss this in just a moment, but what's happening here, right? This is the simplified version of regef. So let's say we have a set U in ZQ to the M of size at least 2 to the K. Epsilon is going to be greater than 0. And K, where am I using K? Let me see. K, you have size 2 to the K, K is here, right? And let's say K is greater than n log Q plus, well, this term, this additional error term. And now let's choose a matrix A uniformly from ZQ to the M times N. And let's choose U uniformly at random. Then it holds that, you know what? Let's simplify that even more. I don't know why I kind of updated this, but good. Good. You know what? Let's get rid of this first sentence here. And let's just say, let's also get rid of this K. And let's just say M is greater than n log Q plus this offset here. And X, yeah, this is actually how regef writes it. We just say X is chosen from 0, 1 to the M, right? X is chosen in exactly the same way as we choose X in the encryption scheme. So this extra generalization is not necessary. And now I'm gonna give you A and X transpose A, right? So X is still this binary vector. And what this lemma says is that A comma X transpose A looks like a U, right? So even if you know the matrix A, since sort of here you're gonna be given this vector X, and you're hashing it down into this shorter vector. Let's call it C, right? We're taking M bits here, Nope. So we're coming from m bits and hashing it down to n bits, right? So you give me an m-bit binary vector and compress it into an n-bit ZQ vector, right? Then the claim is if I started with a random binary vector, then I'm gonna get a random ZQ vector. So let's quickly just do the sanity check. This is not a proof that this works, but how much information is in a m-bit binary vector? How much information is in there? I mean, it's in the word an m-bit binary vector. Yes, m bits. Perfect. So an m-bit binary vector encodes exactly m bits. Good. So how much information is in a ZQ vector of length n at most? Yes? It's a ZQ vector, not a bit vector. So you're having n. So each symbol comes from ZQ, and you're giving me n ZQ. N log Q, exactly. So the information in a and here this is in ZQ to the n, and this is in 0, 1 to the m, right? The information in those two should be exactly the same, right? But so one should say, okay, X is uniform. Now I'm going to hash it down, get something out that should encode the exactly same amount of information. It's not that easy, right? Because the matrix hashing down with this matrix A could lose information. But the leftover hash lemma says that, well, let's make it that M is just a tiny bit bigger than n log Q, right? N log Q, again, is the information that's in this, in a uniformly random element in ZQ to the n. Let's just make the entropy of this vector x a little bit bigger. This by this additive term 2 log 1 over epsilon, right? This can be something arbitrarily small. We just need that epsilon is negligible, right? So this is just let's say what we're asking here is something like 128 extra bits additively, and that's all. Maybe a bit more, maybe let's say 160, but then we're good. Then X transpose times A is actually uniformly random, right? And these hash functions are obviously, when I hash with multiplying with a random matrix A, obviously isn't a good cryptographic right? Finding collisions for these things. Oh, for this one, actually, it's not easy. I mean, there is actually a hard lattice problem hidden in there. So be careful here. But in general, these so-called universal hash functions, right, which can be something as simple as multiplying with a random matrix, typically they're not collision resistant. Again, this one here is going to be collision resistant. But I won't have time to get into that. So, but those were sort of the first hash functions that were invented, right? So long before people tried to use computational hardness to make hash functions collision resistant, this started maybe in the 60s, but really in the 1970s, right? That people realized, wait, we can make it computationally hard to form collisions. All they wanted is that a hash function, right, distributes items well. I think you have a process that generates bit strings, and you would like to map them into bits. right? This is still how bucket sort works. You're going to get, you're going to have items and you want to map them to buckets. And let's say you only have a small number of buckets. The way you typically do that is with a hash function of this type. It doesn't need to be it can actually not be a cryptographic hash function, but you would like that if the input distribution is, let's say, has entropy, is somewhat random, right? If the elements that come in that you map to buckets are somewhat random, then you would like your items to be uniformly distributed into bins or buckets, right? And this is exactly kind of what this leftover hash lemma says in its generalized form. This is now a very simplified form. In generalized form, it says, assume you have a process which produces random-ish elements, and good. Now let's how many bins do we kind of or how many bins can we have at most to distribute them to uniformly? Well, this says like this n log q, right? And I mean, again, you could make q 2 here, but the main feature of these such universal hash functions is that give me a high entropy distribution, right? Hash it down, and you're going to get a full entropy distribution. This is precisely characterized by this leftover hash lemma. This was only formally proven in 1989, but people have been using this at least since the 1950s, right? Without a proof, so to speak. They were like, yeah, it's clearly it works. Why prove it, right? Only when people started using it for crypto were they like concerned, is this really true? Can we really do this? Is this hands-on approach really working? And as a matter of fact, it is, right? The proof is non-trivial. This actually relies quite a bit on Fourier analysis, right? So the proof of this statement is or it needs at least a little bit of Fourier analysis, but it's not very deep math. And now, basically, the condensed version of what I just told you, right? Here, hashing refers to compressing a long string X into a smaller digest X transpose times A, right? More general class of a universal hash function, which, as a matter of fact, offer collision resistance against adversaries who do not see the hashing key A. And this is particularly true if the adversary, the guy who chooses X, is just a random process that's completely oblivious of A. Good. I mean, this also plays an important role in the theory of randomness extractors, right? Which is also essentially another manifestation of the thing I just told you. You have an object, a long string where you know there's randomness in there, but you don't know where it is, and you'd like to condense it into a shorter string that's uniformly random, right? This is precisely what a randomness extractor does. Yeah, now obviously I'm not gonna do a Fourier analytic proof now, but let's wrap this up in the next 10 minutes also. So armed with a leftover hash lemma, we can now prove security for the RAGF encryption scheme, right? Assume that now my m is greater than n plus 1 times log q plus, let's say, to lambda, and the decisional LWE problem with parameters n, m, and q hold with error distribution chi, then the RAGF encryption scheme we've just seen is in CPA secure. And a condensed form of the proof, we're just gonna do 3 hybrids. H0 is the real in CPA experiment, and in hybrid 1, as I alluded to earlier, what we're going to do is we're going to use the LWE problem and replace the public key by uniform randomness. Right? So in the in CPA experiment, we never need the secret key. So first thing we're going to do is we're going to take the public key, which is this A and AS plus E. we're just going to replace AS plus E with uniform, right? We choose B uniformly random instead of AS plus E, and this follows very routinely from the decisional LWE assumption. This is exactly what it says, right? AS plus E looks, given AS plus E looks like a uniformly random string. Good. And now we're in hybrid 2. We're not yet done with the security proof. Now we've just replaced the public key from having a secret key to not being able to have a secret key because it's only uniformly random now. So it doesn't yet say that the ciphertexts hide the messages. But now we're going to do the following in hybrid 2. We compute the challenge ciphertext differently. We just choose R1 and R2 uniformly random and set C1 to be R1 and C2 to be R2 plus Q over 2 times M. What can we say about the scheme now in hybrid H2? What are we doing here? What does encryption do here? So first off, R1, we just set C1 to a random value. That's not going to be used anymore, right? Because C2 doesn't rely on R1, and R2 is independent of R2 is independent of R1. And what's happening in the second step? R2 plus Q over 2 times M. What's that? Yes? It's uniformly random. How do we call this type of encryption? By taking a message and just adding a uniformly random value on top. How do we call this? Huh? No, R is this doesn't come from a noise distribution. So what's the yes? It's the one-time pad. Good. So what we're really just doing here is a one-time pad, right? And therefore C2, if R2 is uniformly random, then R2 plus anything fixed that's independent of R2 is also uniformly random. That's just a one-time pad, right? So once we're here, we know that this is secure by OTP. Good. So this is actually what's written here, right? In H2, the challenge ciphertext is just distributed uniformly random and independent of everything else. Therefore, the adversary's advantage in H2 is 0. Okay, so we've seen the step from H0 to H1 was using LWE. So what's missing is going from H1 to H2. What are we going to use for that? What haven't we yet used? It's the leftover hash lemma, right? The thing, the tool I just introduced. Whoa. Oh my God, why is there so much stuff happening? Good. Let's see. I want to do this in the next 5 minutes. Okay. This is the good. I see. This is the reduction to LWE, and good. This is what I hand waved over. This is all fine. This is just with a few extra details. So what we're really interested in is that H1 and H2 are statistically close, right? And yeah, here comes the definition of what it means to be statistically close. Essentially, no unbounded distinguisher can tell these two distributions apart better than with advantage epsilon. Good. So here we're choosing x from 0, 1 to the m. Good. R1, R2 are just chosen uniformly from ZQ to the n plus 1. And my A prime, which is AB, is now uniformly random because A is uniform and B is uniform, right? Recall that we did this first hybrid step where we replace B which used to be AS plus E by something uniformly random. Good. So important thing here is A prime is uniform in ZQ to the n times n plus 1. Good. So consequently, it holds by the leftover hash lemma that A prime and X transpose A prime and A prime comma R prime have statistical distance at most 2 to the minus lambda, right? This can be rolled out, but again, here I'm going to define the predicates, but this really just says that the ciphertexts that I have in H1, which is this form, H1, and this is H2, that they're statistically close, right? Not even an unbounded adversary can tell them apart. That's what this says, and that concludes the proof. All right, good. That was kind of a run through that, but yes. Yeah, where to go from there? What was I not able to discuss due to, let's say, unfortunate, let's say, missed lectures due to travels, due to holidays and whatnot? I had I think I counted at least 3 lectures less. And also, let's say, my own pace maybe dropping, right? I had at least 3 lectures less than what I did last time I gave this course. I mean, why introduce lattice-based cryptography? Well, lattice-based cryptography led to one of the greatest achievements in the last 20, or let's say in the last 30 years in cryptography, right? Because it gave us fully homomorphic encryption. We've seen the BGN encryption scheme, which allows us essentially to evaluate polynomials of degree 2 homomorphically while getting compact ciphertexts. Now, learning with errors, right? That was a great breakthrough that happened in 2009. Back then it wasn't from learning with error, from another lattice problem, but people realized that when we're using, let's go back to RegF here, when we're doing lattice encryption, we're not using a complicated structure. We're using a simple structure, right? Vectors over finite rings, a simple algebraic structure with noise. And particular, we can use representations of these objects. When we use DDH, we're taking sort of a simple structure, a ring ZP, and map it into a let's say, confusing looking group, right? Into some cyclic group, but that's not what's happening here, right? So the ciphertexts in this scheme still come from a relatively simple algebraic structure. So what people realized is you can actually take advantage of being in a simple structure and do stuff like, well, you're computing with numbers, then do stuff like using their binary decompositions, right? And that's turned out to be the most powerful trick in lattice-based crypto whatsoever, just taking ciphertext and turning them into their binary decomposition. The important aspect really coming down to 2 things: reconstructing a binary decomposition into, let's say, the full domain vector is just a linear operation. And binary decompositions are, well, short, kind of like this X here, which is binary, right? So they don't make errors explode, right? This in itself, in retrospect, was enough to build fully homomorphic encryption schemes from lattices. In fact, the fully homomorphic encryption schemes, a very simple one, the one of Gentry, Sahai, and Waters, is just a variant of this regF encryption scheme, right? You take this regF encryption scheme and let's say you don't just encrypt the bits M once, but something like M times. Encrypt M times, and each time with a different scaling, let's say M multiplied with a different power of 2, and you can show this scheme is already fully homomorphic. You can do arbitrary computations on encrypted ciphertext, and that's typically the exciting end of this lecture, which I didn't get to reach this time around. But okay, I see many people are here to take the second quiz. So let's maybe scooch a bit apart if possible, just for that, and for those who haven't yet. Oh, who wants to take the quiz? So who wants to hand in the quiz? Hey, who doesn't want to hand in the quiz? Then you guys maybe come in front, or yeah, okay. Just technically, it's just a scooch apart. It's just sorry. Anyone still needing one, or does everyone have one? Good. Let's say, you need one. Good. Yeah. No, cool. No problem. No problem. Okay, everyone who wants one has one. So, the extra pen. Good. I did actually. Good. We will just stop at 45 when the lecture is over anyway, which is in 10 minutes from now.